Hi, and welcome to this edition of the ONF Spotlight series. Today we have Hagen Woesner, hopefully I did that as close as I could, presenting on open source BNG architecture and performance evaluation. Hagen is the co-founder and CEO of BISDN, the Berlin Institute for SDN, which is a software company in Berlin. BISDN works on telecommunication applications around white box OS. Hagen's background is quite extensive, working in several places around Europe and founding this company with a group of friends. So welcome, Hagen, and here we go.
Thank you, David. So I'm going to speak about a thing that we did recently in collaboration with Intel, and Intel helped us greatly on tweaking the performance in terms of really getting the best out of a completely commercial off-the-shelf, so mass market hardware. So the exercise that we wanted to do was, if we would not have any special hardware developed at hand, how much can we get out of open source and standard hardware? So that's the frame set here. And I'm doing only one motivation slide, and that goes back a bit in time, like 6-7 years, when people were excited about a thing called NFV, Network Function Virtualization. That was actually motivated by, oh, we have to bring our costs down as telecom operators. Let's learn from the hyperscalers. Let's build our telecom applications just like web servers. The little problem in this one is that while a web server is, or web service in general, is an end of wire, telco applications almost all the time are bumps in the wire. So that means you need to not only get your traffic in but out at the same time. So you at least have twice the bandwidth requirements in terms of I/O to and from your data center. That means you need a much higher throughput. So how can we get throughput? Throughput can, in general, be done or accelerated using at least, let's say, 3 ways. One, you can definitely speed up packet processing in a server using whatever Linux kernel circumvention by using DPDK or VPP. There's recently also a lot going on in BPF, eBPF. That means also using kernel functions to actually speed up packet processing performance. You can also then actually go and push out the user plane traffic from the server and handle it further away, handle it further in hardware. So there are options of getting about a 10-fold increase in speed in the server itself, but then there's another 10-fold increase if you do things on FPGAs, and there's even another 10-fold increase from the FPGA to doing packet processing on a programmable ASIC, i.e. a switch or router. Applying this to a BNG is what is recently attracts recently a lot of attention. I think ONF has started with the CEBA architecture some years ago, and the biggest focus was on getting the OLTs done, harmonized in terms of hardware treatment, in terms of OMCI treatment in the Volta architecture, and recently focus has shifted a bit to the more complex beast, and that is the BNG. And if we look at the options that I mentioned before in terms of where are my architectural options, so I can do things on a switching ASIC, I can do things on a server, I can do things on a smart NIC, and there are various approaches to it. Like we, being in Berlin, are close to Deutsche Telekom, so there is a certain project inside DT which has gained quite some publicity that is pushing forward on a pure switching ASIC solution. There are other options as well. So you may combine a switching ASIC and an FPGA if you, for instance, don't have enough buffering and shaping capacity on your switching ASIC. This is what is, for instance, happening on a Tofino architecture that I'm aware of as upcoming BNG application. There are other options of, yes, of course, you can put an FPGA into a server, in which case it turns out to be what you call a smart NIC. Also, actually, we did that a couple of years ago by doing the more complex processing parts on the server and doing the traffic shaping, the hierarchical QoS offloaded onto an FPGA that actually was sitting on a network card. So this is an option of doing a BNG. And this time I want to introduce a combination of a switch ASIC and server, which we have considered here. And the switching ASIC here is a very, I wouldn't say primitive one, but a mass market one. It's a white box switch. In this case, from Delta, could be EdgeCore, could be anyone else as well. It's a Tomahawk Plus, so that means it's actually a data center switch. It's not a deep buffer switch. It's not anything super complex or performant. We only need that switch for the fan out, and the whole idea is you do the complex things, you do the complex operations of a BNG inside the server. You do the less complex operations where you can actually get them done better, and that means the forwarding, the actual fan out, pushing MPLS tags, rewriting MAC addresses is something that a switching ASIC can do perfectly. Switching ASICs are not as good as at encapsulating, decapsulating more complex frame formats, being programmable on, let's say, PPP, GTP, anything else that comes in. You always need an additional development. So what we wanted to see, if we use just very like plain mass market stuff, where can we get with an architecture like this? What we needed to do in order to get to some performance was to get into a hairpinning of traffic. That is something that we learned very early on. You will not get enough performance if you start copying packets between ports of a server. If you want to copy packets between ports, take a switch. That's what it's made for. If you want to process, filter, not whatever, that's what ASICs are what x86 or for that matter what CPUs are good at. The slight little problem that we have is to extract the control traffic. There's one way of extracting the control traffic, and that is to look into each and every packet that comes in from the user side and goes upstream, and to see, oh, is that a control traffic? Is that a control packet? Is that not a control packet? But that would already spend too many cycles. So we could resort to a trick that's called DDP, Dynamic Device Personalization of Intel, which is applying a hardware filter into the network card. And that means that my data plane, my user plane traffic is never actually leaving the pipeline, is never actually really showing up in a Linux kernel. We're always bypassing it. We're either running traffic through DPDK pipelines or through ASIC pipelines or through a programmable pipeline on the NIC. So it's a combination of all this that actually gets us speed. In case you have any questions, David. Now this, when you look back into this, so you go a piece through the ASIC pipeline, then you go to where you do the queuing. So you have essentially a queuing stage, and then you go through an ASIC pipeline. It starts to resemble a bit like what we have learned for a P4 pipeline, where you have an ingress stage, then a queuing stage, and an egress stage. We are in our BNG here, not say yet using P4, although the whole programming paradigm is very similar. Well, it's essentially match actions that we are deploying, and I can give some details on this also later. The actual interface between control and user plane is PFCP, and I can discuss that also later, why we did that. So what DDP allows us is we get, so this is a BNG that is specifically done for like German ISPs, where we are mostly still using PPPoE and PPP, which is unfortunately way more complex than just using IPoE. So we have the problem of actually filtering out both the PPPoE control traffic as well as PPP control traffic, and all of that can be done in this hardware filter called DDP. And then we're pushing traffic into single instances of either an upstream pipeline or a downstream pipeline. So both of them, an upstream pipeline and a downstream pipeline, makes up together a little BNG instance. And I can run multiple BNG instances on a physical port. And that allows me to scale and actually deploy as many pipelines on as many cores as I want and as I need. And I'm going to present some measurement results later on to justify this scaling here. What we eventually did on a standard server, we scaled up to 16 parallel BNG instances on a server and had 2 instances per 25 gig ports. And that gets us essentially loss-free traffic, and I can present why I'm saying essentially later on. I think on the DDP, I have already spent some words. That allows me, that's I can load different profiles into the network card. Those profiles can extract GTP, C or PPPoE, PPP control traffic, or IPsec. So that's a loadable profile. And then the actual pipeline that runs attached to the input queue, the RX queue of a virtual function, so of a virtual network interface. On the left-hand side, you essentially see that you have a double tag traffic coming in. So that is the access side of the traffic. And on the right-hand side, we see the 2 VLAN tags removed. In the meantime, the traffic passes through flow classification, some metering, policing, a routing, which essentially means I have a certain 1 or 2 uplink. So I need to rewrite both source and destination MAC address. All of that is happening in an uplink pipeline. There's a downlink pipeline which looks different because mainly it has a hierarchical QoS inside. We can also have more functions in an uplink, which we then call the full config, which would then also include NATing. It really depends on what the customer wants, on what the ISP wants. We can put in various functions into that pipeline. That, for the sake of completeness, a full config downlink pipeline would look like this. Just as an example of how you would program such a pipeline. So this code is, it comes with DPDK, so the open source way of programming a data plane pipeline, and it comes as one of the examples of DPDK. We can create tables, and we're essentially linking tables into a whole pipeline, and those tables underneath call DPDK library functions. So this is how we are then creating a full pipeline out of various library functions. And then eventually you would, like down there, when you go to the pipeline blocks, you see pipeline downstream routing table 0, rule add match, default in this case, and then you have action forward drop, or you just forward it to some output place. So it really looks, to those who are familiar with OpenFlow, it looks pretty much like OpenFlow. or before runtime. This is similar. We do separate control from user plane in that sense that we are encapsulating the control plane traffic into a VXLAN tunnel, send it off to wherever centralized server we want to have. The actual control to user plane protocol, we're using the packet forwarding control protocol, PFCP, for this. And that means that we are following the broadband forum specification on this side. That's probably arguable, but that is, I think, the most advanced standardization of a control user plane interface that I at least have seen so far. So we're actually having two interfaces. One is pulling up the control traffic, and to be precise on this one, this is the PPPoE control traffic that sends the discovery packets and then gets an offer, sends a request, and gets a session assigned. So it's a two-way handshake to actually establish the first PPPoE session. And then following that, there is a lot of link control protocol, network control protocol, IP control protocol inside the PPPoE session that actually then establish the PPP session. So it's a lot of traffic that we're pulling out from the network card, encapsulating it into just a VXLAN tunnel. So we don't work on that traffic. We're not pulling it through a P4 runtime interface. We're not pulling it as a packet in. It's just plain control plane traffic that goes up into the control plane server, and that control plane server uses the session requests and session responses from the original. So PFCP originally comes from 3GPP, and some extensions to PFCP have been standardized in the Broadband Forum 459. So we're using this, and then basically you get a session request from the control plane to the user plane, and the session response from the user plane to the control plane. But the whole initiation of the session requests comes through a separate interface, which is just the control plane interface. It's probably too technical here. Let me come to some fancy measurement results. So we've done we have very good friends at Deutsche Telekom that were offering us the use of their Spirent for a limited time, so we could do some decent measurements on 2x100 gig ports. That's something that you can normally not afford as a small company, but yeah, it was possible to do it here. So what we did was to split the 2x100 gig inside the switch into 8x25 gig. Then we used Intel 25 gig, so two Intel four-wheel cards, standard cards, nothing fancy on it, and not expensive at all. And so that's just standard hardware that you can find in any data center as well. So then we went into a lot of tuning and queue dimensioning and so on, and eventually identified three bottlenecks, which is one, of course, the DBDK IP pipeline itself. So that is basically how many packets you can push through a core. Then there's another one, which is the ASIC in front of it. And then there's something in between the PCI and the CPU. So we've seen some practical limitations of the PCI bandwidth going into the CPU. That, I have to state, was just, we only did our measurements on one server, so I can't really say that this is a general thing, but this is what we have done. What we noticed first is that a single upstream and downstream pipeline can't just quite serve a full 25 gig. So we did some comparisons, and then eventually just decided to potentially you may want to take just two and attach two pipelines to the same virtual interface, and then you get what you want. Just what it means: an upstream pipeline takes one hyper-threaded core, downstream pipeline takes two hyper-threaded core. One hyper-threaded core is just busy with doing the HQAS the hierarchical QoS, the traffic shaping, and all the rest can be done by another hyperthreaded core. So in essence, it's 1.5 physical cores per BNG instance. I have some measurements here, and I'm rushing through these because we have limited time. Essentially what it means for 4K sessions, a single instance, so 1.5 physical cores can process 5 megapackets per second in the downstream and plus some in the upstream, but we're only considering downstream here. And 2 instances can, not surprisingly, process the exact double. And that means with 22.2 gigabits per second at 250 size 56 byte packets, we are essentially at line rate because we are not measuring the upstream here. So basically loss-free at line rate can be achieved with 2 instances. The important part here is that this also has implications on the achievable delay. The normal comment when you say, oh, we're doing some packet processing on x86 is, oh, wow, that's slow. It is not. It is not necessarily slow. We eventually can, this is a comparison. So I have put a dashed line here at 1 milliseconds. So you see that we have a working range depending on the number of sessions that we're processing, and depending on the size of the frames that we're creating, and all of that is pretty conservative, so pretty short packets actually. We have a working range that is on the area of 70 microseconds if we run 2 instances. So that's below 100 microsecond, and then you add another 7 microseconds for going through the switches, irrespective if it's a Mellanox or Broadcom switch. We try both. So you can get pretty low in overall packet processing delay with that. And what we ended up doing, and that is also then basically taking into account that we have more than the bottleneck of the individual DPDK pipeline, but some more bottlenecks in either the NIC or the PCI. So what we could show is that we can fill up each 25 gig port up to 20 gig, and then have 8 ports on this, and you get 160 gigs of traffic, lossless, implemented on completely standard commercial off-the-shelf hardware. So what my point here is, delay is maybe not so much of an issue, but moreover, it's actually manageable. If you have enough cores, if you're willing to pay in terms of energy consumption or hardware investment, you get down very low in delay. So for us, like the working range of 70 microseconds is absolutely acceptable. At least this is what I heard from our customers. So so yeah, it's essentially possible to get 260 gig on a server. What that means for us, we can split stateful forwarding functions from stateless forwarding functions. And that stateful forwarding, first of all, means hierarchical QoS and NATing. And my point is that this stateful forwarding can easily be put, and should actually be put, into CPUs, whereas anything that's stateless could and should be separated into relatively simple white boxes. So this is giving a position in a currently ongoing discussion that I'm perceiving partially in the ONF, partially in TIP, the Telecom Infrastructure Project, of various architectural approaches, where some companies are pushing for purely on-switch solutions, and others are pushing for a more VNF or NFV-inspired functions. The point that I'm trying to bring in is, yes, it is possible to get to performance with standard commercial off the shelf. that is it from my side. If you have any questions, David or anyone else.
Okay, first of all, that was great. Lots of information there. It was interesting as I was listening through it. I was coming up with questions around thinking about scaling in this, and you actually hit on a lot of the points that I was thinking about, particularly around what were the bottlenecks. You talked about the DPDK, the ASIC, and the PCI CPU link as one of the bottlenecks. As you got up to 16 parallel BNG instances, so that is that a place where you're going to see some future research or experimentation around there to understand those limitations better, and or how you might be able to work around those?
So I first of all should probably say that the servers that we had were by no means high end. So
Okay.
this is like a, the CPUs are 2017 CPUs. So um, I see completely different values from Intel. But so I believe that some of the bottlenecks that we have are already gone.
Okay.
But or maybe and I maybe don't know. But that is, I think, on getting over the bottlenecks. We used to do the extraction of the control plane traffic in a soft switch on the server. That is what we did in a previous architecture. And that got us, and we were super excited to go to 100 gig. So just the fact that we can now on the same hardware extract the traffic on the NIC, the control plane traffic, gets us to 160. So that is, I think, more important to get rid of, basically to be able to keep the packet processing in the DPDK pipeline and not have any other extractions into servers. What I believe is more important for me now is to get into a better programmability. We want to extend the programmability of the individual pipeline. Right now, all of that is statically deployed. I mean, we are putting that into bare metal Kubernetes containers, but this architecture gives room to have various protocols side by side. So I can have a GTP pipeline if I want to be running that in parallel to a PPP pipeline, in parallel to an L2TP pipeline. Whatever comes in, I could actually dynamically deploy a pipeline for that and handle all sorts of incoming traffic. And I might even be able to reprogram my pipeline on the fly, saying, adding, I don't know, adding nutting functionality for only a subset, or providing something like a virtual routing function to individual customers, and even provide that API to a customer to say, here you can put your own routing entries, here you can put your own ACL entries, and it's running in the hardware. So this programmability is what is really, I think, when we speak about research and speak about going forward, that is what we want to do next, and what we will do next.
Oh, that actually sounds really great, because I think when you look at a lot of the programmable chips, right, it's a process of, program it, restart things, run it for a little while, program or restart things, right? The cycle's disruptive. And as you look at that kind of how can we do that dynamically, it becomes very interesting and a very powerful thing. Do you think that kind of the programmability of these switches today is one of the adoption problems that you're running into? It's still kind of a complex process to get this programmability in there, to get the BNG functionality up and running, versus if I'm an operator, for instance, I need to make traffic work. I don't have the resources or perhaps the expertise to kind of do this programmability.
Certainly, I think you don't want to recompile your P4 program in order to add a certain, I don't know, parameter. And I think most operators will lack the expertise to do so and need something pre-configured. But at least with this one, we can give quite a tool set, or quite a set of working blocks that where you can say, oh, I want this table, and I want this table, and I want that in my pipeline, and please put it there. And then there is an overall control plane, and this is the let's say, it's easy to say, yeah, we're combining a switch and a server, but you need to program them at the same time. So you need to say, oh, there's this double tag, and I have just changed my scalability. I just deployed my pipeline elsewhere, so I need to also reprogram the switch that puts traffic in and out there. So there's quite a bit of control to user plane interaction necessary here. But we can provide building blocks, and this is, I think, easier to digest than requiring programmability from an operator.
Do you envision, in terms of that programmability, those building blocks more along kind of towards the intent type interfaces that we're seeing today in network management even?
I think so. It will be more of, yeah, give me HQuas. Give me give me HQuas for 16,000 customers, 3 levels of HQuas, 8 counters. Here you go.
Okay.
And put traffic in there, and give me an interface which lets me configure at runtime that specific function. So I think the whole combination of the pipelines would go in those building blocks that are intent based. But intent based not in the sense of I want to get traffic from here to there, but I want to get traffic handled in this particular way.
Yeah, exactly. Now how does that balance against, again, scaling and performance? When you get to kind of the intent, sometimes users will specify intents or the automation to go from their intent to the actual physical program. You lose some of that performance. You lose some of that kind of micromanagement of the pipeline. Any thoughts around how to handle that so that the intents actually are optimized once they hit the pipeline?
It's essentially a routing problem that we have here, and we want to. So far, I mean, as you could probably guess from the talk, everything is pretty static up to now.
Yeah.
We are already seeing, even like in the very primitive ways of, I want to take down one server and redeploy it. Yep. So I need to put a lot of my sessions at the same time, put them onto a different server. Already that is very difficult because my session is stateful. My session is full of counters. I have practically no way other than disrupting it and setting it up again. It's just control user plane separation sounds easier than it is in terms of maintaining session state. Essentially, you are necessarily abstracting session state to eventually a binary session up, session down, but you need to know much more. And the more you need to know, the more bulky gets your control user plane interface. All right. I mean, yeah, that was trivial, but still it's a problem.
No, fair enough. One last question about troubleshooting. One of the problems operators have with any network equipment is if something goes wrong, how do I understand what happened and how do I go from where I am now back to an operational state? Have you looked at troubleshooting some of these pipelines and how that works in an operational environment? Again, I understand that a lot of it's static today, experimental, but any thoughts around that?
I mean, we do know something around Kubernetes, so we can at least supervise the building blocks. We can at least supervise, oh, there is an upstream container that went south. So I need to redeploy that one. And like really coming from the cloud thinking of, yeah, I don't really care. Yeah, I just lost 4,000 sessions, but I may need to put them elsewhere anyhow. But I mean, using Kubernetes on that side for troubleshooting is what we're used to doing.
Okay. Does that mean you're almost taking more of a kind of the fast fail mentality around some of this as opposed to recovery?
I mean, as long as they let us.
As long as
So
they
it really, let's see who is tolerating it. So this is also what I wrote earlier. The customers that we target are smaller ISPs and not yet the big telcos. That's not because I'm thinking that the stuff is unstable that we do, but I think it's the mentality of not being able to fail that has to change on this one. And I really think that a customer doesn't really mind if you're bringing the session up in the next 4 or 5 seconds, and if it doesn't happen like more than once a day. But
right.
but I think customers are probably more tolerant to short time failures than a big telco might think.
As long as it doesn't, happen right when the winning goal in the World Cup's happening, I would kind of agree.
Yeah. There won't be any World Cups anymore anyhow. So
There you go. Okay. Anyway, again, thank you very much for this presentation. It was very good, very informative. It was actually excellent. I looking at some of the background thought around, okay, why aren't more people thinking this way? It is interesting trying to that combination of the x86 taking better advantage of those hardware pipelines, and looking where that balance is. So really appreciate the talk today. Thank you very much.
thank you very much, David.